Welcome to This Explainer. Today, we're doing something really cool. We're going to completely peel back the layers and take a look under the hood of massive industrial operations. We're going to explore the concept of digital anatomy, specifically focusing on the systems that keep everything from chemical plants to power grids running flawlessly, day in and day out.
We've got a lot of ground to cover today. Here's our roadmap. We're looking at the blueprint of the APL, data DNA, the brains, the muscle, and finally, engineering at scale. Let's get right into it.
All right, let's dive in. Picture this. You're managing literally millions of data points across a sprawling factory floor. You absolutely cannot rely on guesswork, right? You need a rock-solid, completely unified system to maintain control.
So before we go any deeper, let's get our terms straight. The Advanced Process Library, or APL for short. What is it? Well, it's essentially a highly standardized modular toolkit. Automation engineers use it to make sure plant operations are safe, efficient, and consistent. Honestly, think of it like a set of highly engineered Lego bricks. It guarantees everything snaps together perfectly every single time. Section 1. The blueprint of the APL, the foundation of consistency.
Now, to bring some vital order to what could, frankly, turn into total industrial chaos, we use standard functions. Things like interlocks, operating modes, and alarms. These actually act as a sort of communicative shells surrounding every central technological block. By wrapping this identical hub structure around every single motor or valve, we get a strictly consistent operational philosophy across the entire library. It's brilliant. Moving on to Section 2, Data DNA, Value and Status. Okay, we're zooming way in now to look at the digital DNA of the factory floor. Keep in mind, misreading just a single temperature signal in a chemical plant could literally mean a physical disaster. That's why in the APL, data isn't just some naked number floating around. It's more like an armored cable. The value tells us what the number actually is, but the status tells us if we can actually trust it. They are completely, inextricably linked, traveling together everywhere as a comprehensive 2-byte package. And that brings us to this priority ladder, which evaluates exactly how trustworthy that data is. Now, here's the absolute key takeaway. The worst status always takes the highest priority. Why? Because you never, ever want to accidentally mask a critical failure. For example, priority 1 is a bad device-related error. Basically, something is broken. But check out priority 0, sitting at the very top. Simulation. That acts as the ultimate manual override, superseding even a total device failure.
So, what does this all mean for the system? The crucial point is how this status information propagates through the system's logic gates. When you're looking at an AND gate, the system acts pessimistically. The output just grabs the worst status of all its inputs. It assumes the highest level of risk. On the flip side, an OR operation acts optimistically, outputting the best status of the inputs that have a value of 1. It's a pretty fascinating look at how digital logic inherently manages real-world uncertainty, isn't it?
All right, Section 3, Brains, Customizing Block Behavior. This is where things get really cool. This is where engineers take those highly standardized blocks we talked about and custom tailor them for specific industry needs. They use something called a feature parameter structure. It's essentially a 32-element Boolean checklist that allows engineers to completely change a block's behavior, like toggling it between a push-button mode or a switch mode. But the real magic here, they can make these dynamic, industry-specific tweaks without ever needing to stop the automation system. Talk about a game changer.
Section 4. Muscle, Core Automation Blocks.
Shifting our focus from the brains to the brawn, let's look at blocks like the MLC, or Large Motor Control. Listen, this isn't just a simple on-off switch. It has to handle complex, real-world physical delays. For example, check out the warning times feature. It actually delays the start command just long enough to trigger a pre-warning horn or a flashing light before a massive physical drive actually spins up. You definitely want that heads up. And then for valve control, we have the VLVL block, which handles the very real, very scary threat of industrial power loss. This block is basically programmed to know the physical safe position, or safe pause, of the valve controls. Whether it's safer for a pipe to fail completely closed to stop a chemical leak, or maybe fail wide open to vent dangerous pressure. Well, the block automatically defaults to that exact state if the control signal ever drops to 0. Which brings us to an absolute, totally unshakable directive in this environment, the golden rule. It is contrary to the philosophy of Pcs7 to place other blocks between the drive block and the output driver. Look, you do not mess with this rule. No way.
It is an unbreakable engineering best practice, and it's there to guarantee direct, safe, and instantaneous control over the physical hardware.
To round out our muscle section, we've got the continuous PID controller. This is a prime example of incredibly complex, automated mathematical correction happening right in real time. It's just constantly calculating and adjusting based on internal or external set points to keep the entire physical process perfectly balanced.
But, as you might guess, all this intelligence comes at a computational cost, and that introduces a classic engineering dilemma, the footprint strategy. When exactly do you use a large block versus a small block? It's a constant balancing act, choosing between having every possible bell and whistle or saving precious CPU memory and cycle times. The trade-offs here are actually incredibly clear. Large blocks offer maximum functions. We're talking full alarming, complex interlocks, but they absolutely eat up memory. Small blocks, on the other hand, offer reduced functionality to save runtime resources. The main takeaway? You simply don't always need full, complex functionality to solve a simpler automation task. Sometimes, efficiency is just as critical as capability.
All right, final stretch. Section 5, Engineering at Scale.
So how do we safely and reliably multiply all this micro-logic across a massive, multi-million-dollar plant? The answer is templates. Now, a template isn't just the core technological block we discussed earlier. It is the entire, fully prepared chart. It contains the input drivers, the interlock blocks, the output drivers, literally everything necessary for a complete, fully functioning, real-world component that's just ready to be duplicated.
Once scaled up, the whole facility needs to communicate seamlessly. That's where the integrated alarm generation comes in, acting essentially as the digital nervous system of the entire plant. Process messages are generated centrally, right inside the automation system, and then they're instantly broadcast to all logged-on operator stations. That ensures everyone, everywhere, sees the exact same critical alerts at the exact same time.
Now, all of these safeguards, logic gates, and alarms, they're incredible. But I want you to consider something. What happens when the hardware fails entirely? Imagine the ultimate worst-case scenario, where the physical hardware just completely breaks down. How exactly does the logic protect the physical world then?
The answer actually lies in explicit OR gate interconnections. These act as the ultimate automated failsafe. Let's say any single driver output receives a bad status, meaning a value of 1. Well, that highest priority bad status propagates straight through the OR gate. It completely bypasses everything else and leads to an immediate, hard shutdown of the technological block. It prioritizes absolute safety above all else, unconditionally, no questions asked. Which leaves us with this final thought. In these massive industrial systems, a single error can mean catastrophe. That's exactly why they demand that every single data point carries a status, proving its absolute reliability before it's ever acted upon. So, if industrial systems demand this rigorous level of verified truth, shouldn't the data we consume every single day in the rest of our digital lives be held to the exact same standard? Something to think about. Thanks for joining me on this explainer today. I really hope you found this deep dive as fascinating as I did. Catch you next time.